So I didn't actually compute the average grade, um, but I think it was somewhere around 170 out of 200. So that would be a 85. That's a pretty good average. All right, any questions on recursion before we dive in? Cool. Recursion in itself is a fairly simple topic, but using recursion and writing recursive methods is where the complicated part comes in. Sometimes it is difficult to think in a recursive context, but recursion is not much different from a loop. Anything you can do with recursion, you can also do using a loop. Anything you can do with a loop, you can also do with recursion. And the first example in this chapter is something that I think is much easier done in a loop. My go-to strategy for accomplishing that would be with a loop. And that's, let me remember what order. So, So the first thing we need to do is get some digits. Okay. So we have now gotten some integer with many digits from the user. Let's see. How many digits does this number have? In the book, it has 4. So I'm going to say that we should be able to take an integer with an arbitrary number of digits. let's do that. We're going to start at the end because we know there's going to be at least one digit that we're going to print, and create a temporary string and append or prepend the previous digit to that. So we'll start at the end, just like the book does, except we're using a loop, not a recursive call quite yet. So we'll create a string called string to print. Initialize it with the empty string, and we'll start by taking the last digit and prepending it to this empty string. So that would be some number mod 10. Right? Nope, not plus equals. Prepending, not appending. That empty string there is a hack to ensure that we're turning that integer into a string. Adding an integer to a string makes a string, but adding a string to an integer, a string on the right-hand side of a plus sign, integer on the left-hand side of a plus sign, causes a compiler error. And just to ensure that everything happens in the order we want it to, we'll put some parentheses there. And the last thing we'll do in this loop is divide some number by 10 and store it back in itself. So if we enter a number 1, 2, 3, 4, line 12 will turn it into 1, 2, 3. And then on the next iteration of the loop, some number will be 1, 2, 3, and we'll go through the process again. Then on the next iteration, it'll be 12. On the next iteration, it'll be 1. On the next iteration, 1 divided by 10 is 0. So some number will not be greater than 0 and will drop out of the loop. And at this point, we can however, so far we don't have any new line characters. So we'd end up printing out exactly the same number that we got as input. So let's actually make this useful. Put a new line character there. Does anyone disagree that this should accomplish the same thing as what's in the book, just without using recursion? Let's first make sure it works on the input the book uses. And it does. Let's see if it works on something much larger, 65,535. That looks correct. So that's nothing new and exciting. That's using loops. We know how to do things using loops. But sometimes loops are not the best way to think about doing something. And they certainly don't really lend themselves to top-down programming. A lot of times, we will end up with problems that have subproblems. We can solve as subproblems and then put together their solutions into a larger problem. But the subproblems are exactly the same as the larger problem, just a smaller version. And if you have a situation like that, it screams recursion. Have one method dealing with the larger problem and call that method on a smaller problem and have that method also be able to deal with the smaller problem. So I'm going to move this into print with loop. Move this into a method. And in theory, that would still compile and run. And then we can go ahead and do that. And we'll create another method called print with recursion. So this is kind of a contrived example, but if we want to print out a large number, and let's pretend that we don't know how to print out a large number, we can say, I know how to print out a single-digit number on a line. And for, it's kind of for ease of getting the answer, but also kind of an arbitrary decision. We'll say that we know how to print out the last digit, and then we'll call up to some other method to print out the rest of the number. So we can actually reuse a whole bunch of code that we have down here. So we'll say we already have a method, well, we're in the process of writing a method that will print out an n-digit number with all of its n digits on individual lines. So we'll say, call that with most of this number, but lacking the last digit. So print with recursion and some number divided by 10. So some number divided by 10 is the tens digit through whatever the highest order digit of this number is, leaving off that last digit, because we're going to print that in this method. Which we'll do like this. So, as you can see, very similar to how we did it with the loop. The problem that we run into here is that we have something called infinite recursion, just like an infinite loop, except far, far worse. An infinite loop simply never ends. Infinite recursion, depending on what operating system you're running, I won't name names, but depending on what operating system you're running, it might lock it up. Especially if you're using a language that runs directly on the operating system. With Java, we're pretty safe. But infinite recursion is still a bad thing. Basically, that's because every time a method is called, some memory is taken up to represent that method, the fact that it's running any local variables that method contains. So in this case, some number would be allocated every time we call print with recursion. If we call print with recursion 5 times and all of those invocations are running, we would have 5 ints on the stack, on the call stack. that would be taking up memory. If we had a call to print with recursion that had depth of 500, now we have 500 ints on the stack, in addition to other overhead that Java uses to store. So if you get infinite recursion, it's very, very bad. Which means that we need some sort of stopping condition. I think that's the term the book used. Stopping case. I've heard base case. It's basically some known situation where you don't do any further processing, you just return a value. That's all you do. It's similar to this, the Boolean expression that forms the condition for a while loop or a for loop. So with recursion, we need some case that we know that we're not going to go any further. This stops the recursion. So in this case, if some number, let's see, what's the case that they use? They say if number is less than 10, print out the number. That's the case they use. It's really a matter of convention and personal preference, whether you want your base case to be the singular case, the one case, or the empty case, the zero case. I tend toward the zero case. So if I can't do anything, if it's not possible for me to do anything, I just return. That's my base case. The book uses the singular case. So if there's only one digit to print that digit, and that's it. The main difference is that the way I write my recursive methods, I end up with one extra call to the method. But in the grand scheme of things, that one extra call is not going to incur any extra overhead. But I'll stick with the book here. So if some number is less than 10, println some number. However, without any other logic, it would execute everything else. So all of the second half of that method should go in an else. Again, I tend to differ from the book in this respect. I like my base case to basically be a short-circuiting version of the method. So if I hit my base case, I return. I'm done. This method ends. That makes it very explicit that is my base case. If you simply have an if-else block, it could be logic deciding what you're going to do on that particular call of the method, which I guess technically it is. But it's not as clear what my base case is without comments. Here, I don't have to comment this. It's very clear. This is a recursive method because it's calling itself. And that is my base case. If some number is less than 10, that ends the recursion. And the other part of recursion is, the book calls it the recursive call. And I have seen it called that in other places as well. I prefer the term approach, which you've heard me use in talking about for loops. I like that term because it implies I am getting toward my base case approach. It's more active. Recursive call is kind of ambiguous. Of course, being a recursive call, it means it's calling the same method, but it doesn't actually imply that it's going anywhere. So I already mentioned one way you can get infinite recursion, and that is forgetting to put a base case. The other way you can get infinite recursion if your approach doesn't actually accomplish any approaching. So if instead of print with recursion some number divided by 10, I call it print with recursion some number, I wouldn't be getting anywhere. That would be infinite recursion as well. But with this implementation, we do achieve the desired result. And it runs successfully. And we can also print out larger numbers or enter larger numbers, and it still works. So are there any questions on what recursion is? So, this is my approach. Yeah, I can spell. That's my approach. We can call this, I don't know, I'm going to label it actual doing stuff code. There we go. And here's my base case. Just for completeness, to turn this into, this is, I'm calling it singular case. The base case is the one case. I still have something to print out, but I know that after that I don't have anything else to print out, so I'm not going to call the method again. In order to convert this into the what I'm calling the null case, the zero case, there is nothing else. I can't possibly do anything else. So that the only thing in my if statement is a return, which I like seeing that because it makes it even more clear what the base case is. There is a condition and there is a return statement. That's it. And usually, this is especially handy if the thing you end up doing on the one case is exactly the same as the thing you end up doing on every other case. There's really no reason to repeat yourself. So with it stated like this, I only have one call to system.out.println. I don't have, it's less duplicated code. And I know you're going to like this because this is even fewer lines than before. I can put that return statement on line 14 if I wanted to, and I'd have even fewer lines of code because it's so short. Well, I have this extra white space. And then some people could argue that it's less readable. I would argue that it's more elegant and not any less readable. The first line of the method is the base case. It's very clearly stating this is where the recursion ends. And this is the best kind of recursion. If your base case can be stated in a single line of code and your approach can be stated in a single line of code. There are instances where that is not the case, and sometimes it can get very, very unreadable. There is not always one right answer to implement recursion, but there is usually at least one good answer, or one better answer. Yeah, some answers are more readable than others. We'll see some of those when we start talking about trees, which I think is next class. So we'll specifically see recursion with trees because it's a lot easier to write methods to deal with trees using recursion than it is to write methods to deal with trees using loops. With linked lists, I'm kind of skipping ahead at this point, but trees are kind of like linked lists that aren't strictly linear. They branch out. Um, but linked lists, you can also use recursive methods. We used loops because we hadn't talked about recursion, but there's nothing preventing you from using recursion. Calling the same method on the next value of a particular link as opposed to just advancing a pointer or advancing a reference as you go through using a loop. And I didn't compile this and run this to prove that my way still works, but I can. Usually I can. Okay, so apparently I missed something because you can see that's some infinite recursion there. Because that's never going to happen. I'm never going to get it something less than 0. 0 divided by 10 is still 0, which is not less than 0. That's better. So when you get the base case right, it works. And that is something to watch out for. If you're trying to be clever, make sure your base case is actually right. Otherwise, you'll get infinite recursion. Another classic use of recursion, another classic example of using a recursive method is the factorial operation. Is anyone not familiar with the factorial operation? I feel like I used it in an example earlier in the semester. Or maybe that was the other class. It's the problem with teaching 2 Java classes. They kind of mesh together. Yes, switch the example halfway through. There we go, factorial. So, in your previous Java class, was it discussed what this string args thing was? Besides an array, what its function was? Nick, you're nodding your head. What's yes. Usually referred to as command line arguments. This is the way that pretty much all Unix programs work. I usually live at the Unix command line, so I really like command line arguments. This is going to allow me to type the name of the Java class file and specify a number directly on the command line. I'm not doing any error checking. If I didn't specify a number, it would break horribly. But this means I don't have to have a prompt. I don't have to use a scanner. I don't have to get keyboard input. Don't have to do any of that. This program doesn't make any sense unless I give it a number, so I can just get it right on the command line. And integer.parseInt, is that familiar to anyone? I guess I should hope so, since it was part of one of the earlier assignments. I think at that point it wasn't familiar to most people, but that's a utility function, utility method that's part of the integer class that takes a string and spits out an integer. And if it can't, this string can't be parsed as an int, it blows up. It throws an exception. So again, I'm not doing any error checking here. But the basic idea is I'm going to call a method called Factorial, which will private static. The result of a factorial is an int. Unless it gets very, very large, then it might cause an overflow. And the input to factorial is an int. I'll call it in. Who wants to refresh our memories of what the factorial actually does? Nope. Dion, did I use factorial in Visual Basic? It's same thing. Yep. Mm-hmm. Yep. So, we could also do this with a loop. We could start out with the number that we're dealing with, and then increment I or something from 1 to that number, and multiply some running accumulator by that I as we go along. But we can also do this using recursion. Factorial is usually the mathematical definition of factorial is usually written as n factorial equals n times n minus 1 times n minus 2 ... 1. It can also be written, so that's a statement. That's one statement of that, but we can't really turn that into something we can write using recursion. Written as something called a recurrence relation, which is a more advanced mathematical concept. You can give it in two parts. One is it's basically a base case and an approach. The factorial of 0 is defined to be 1. That's your base case. And the factorial of n is defined to be n times factorial of n minus 1. And we can turn that pretty much directly into Java code. So the factorial of 0 is defined to be 1. So if n equals 0, return 1. Base case, done. And then we can actually combine our doing stuff and our approach into one statement, because the factorial of n is equal to n times the factorial of n minus 1. And so in this case, it's the factorial of n is equal to n times the factorial of n minus 1. And that's it. So in Dr. Java, if you are expecting command line arguments and you hit run, it will break horribly. With a seemingly obvious error message, array index out of bounds exception. There are no command line arguments, so args0 does not exist. In fact, args.length is 0. But in Dr. Java, you can say run factorial, which is actually exactly what hitting the run button accomplishes, and then specify your command line arguments. So Dion used the example of 3, so 3 times 2 times 1 is 6, so hopefully we'll get 6. And who wants to make bets on what factorial, how high and what number I need to take the factorial of to get integer overflow? So I need this entire multiplication to be greater than 2 billion something. I think. Half of 4, yeah, 2 billion. So I think it's not 10. Okay, there we go. It's somewhere between 10 and 20. That's pretty close. Factorial of 2, I can. And factorial of 1 is 1. And to test our base case, factorial of 0 also 1. Factorial of negative 200 is infinite recursion. And for this reason, when this is another reason that I use my base case to mean anything that doesn't make sense. So the factorial of 0 is defined to be 1. I usually change this to a less than or equal to, there we go, less than or equal to. So if I end up putting a negative number in there, it doesn't blow up. It's mathematically incorrect, but I'd rather be mathematically incorrect than have my program explode. So does everyone think they get the hang of recursion? I'm going to do one more example, which is actually, besides being kind of cool, it is programming project 9 on page 450. And this is the example that they give. I wrote this right before class. And the idea is take this pattern and turn it into some sort of recursion. So far, we've only had one call within our method to the same method. But we'll see when we get to tables, trees, that because we have multiple branches, we actually have multiple calls to the same method within the method body. And it's still recursion. It just gets a little more complicated. Quick discussion of terminology, which I don't believe is in the book. There is such a thing as left recursion and right recursion. That basically refers to what piece of your overall problem ends up getting handled by the recursive call to the method. The first example with the numbers, or the digits, was left recursion. The rightmost piece was the actual body of that call, whereas everything else on the left side was handled by the recursive call. The factorial, on the other hand, was write recursion. We handled the piece of data that we had when the method was called, and then we took the rest of it and abstracted that out to the recursive call. So everything to the right of it was the recursive call. And if you actually wrote out the factorial of 10 times 9 times 8, you can see that 10 is handled by that first call, and everything to the right of it is handled by the recursive call. When you have multiple recursive calls, you don't really talk about left and right recursion because it's technically both, I suppose. So who wants to suggest an approach? It doesn't have to be in Java code. Just looking at this, how you would take this 8, which is the width of this this whole pattern, and turn it into some set of recursive calls. How would you break this problem down into smaller subproblems that are essentially the same problem? Let's start by talking about the pattern. What is the pattern here? Lynn, what do you see in this? Right. So that's a pattern. Look for a level above that. So that's about the middle level of the recursion. But that's still a very important piece. So what jumps out at me right away is that there's this, it looks like a big dividing line in the middle, this line of 8 asterisks. And then the thing above it and the thing below it are pretty much identical. One of them is just shifted over 4 spaces. And in addition to that, if you look at one of those quadrants, you see essentially the same thing going on. Those quadrants are divided into a top half and a bottom half by 4 asterisks, which at this point it's good to notice anything that seems like a pattern. 4 is half of 8. Might be important. And everything to the top, above that line of 4 asterisks is identical to the piece below that line of 4 asterisks. It's just shifted over by 2, and 2 is half of 4. And before, 4 was half of 8. And then it seems almost like the 1-2-1 pattern is the most elemental pattern. That's psychology playing tricks on you. The human brain is very good at grouping things together that look like they should go together, but if you dissect that, even that pattern, you can see that it too follows the same pattern. There's a dividing line with two asterisks in it, and above it there is a quadrant that is identical to a quadrant that is below it, just shifted over by half the length of that line. So how can we turn that into a recursive call? Yes. And I kind of hinted at it before when I was talking about you can have multiple recursive calls, and let's make sure I don't name it the same thing. Asterisk recurse. Okay. Asterisk pattern will work. I'm going to make a I'll call my recursive method draw asterisks. And we actually have two things going on here. We have a width of the pattern, and we also have some distances shifted over. So instead of just having a single argument to this method, we'll have two. We'll have, so 8 will be our width, and 0 is how far it's shifted over. I'm not going to take any input for this one. So width will be the width of the pattern, and offset will be how many spaces I have to add before the pattern. So let's start at the top level. Our width is 8, and our offset is 0. We need to draw some pattern at the top, then 8 asterisks, and then some pattern at the bottom. So let's start with that pattern at the top. How do we accomplish this? It's a subpattern. How wide is it? It's 4 wide, which we noticed is half of 8. So let's say width divided by 2. And how does it relate to its parent pattern's offset? This top level pattern has an offset of 0. The pattern at the top also has an offset of 0. If we were to look at deeper and deeper patterns, we notice that the subpatterns have some offset that is at least the same as the offset of the parent. So let's start with that. Now we need to draw 8 asterisks. The problem is that when we get to subpatterns, we still have to include that offset somehow. We need some number of spaces between asterisks. And if I can spell things correctly, I'm actually going to write a method called nchars, and give it a number of characters and the character to have n of. So in this way, we'll have some number of spaces followed by some number of asterisks. So the sum number of spaces should be offset, and that should be a space. And the number of asterisks should be width. So let's assume that I've already written n chars. What should go below that dividing line? It's essentially the same as I have in line 7. So we'll start by copying and pasting. How does the offset of this pattern relate to the other variables we have for the parent pattern? So it's shifted over by exactly half of the width of the parent pattern. Conveniently, we have a variable called width. My mouse go. There we go. And now I guess I should probably write that n chars method instead of string n chars. I'm going to do this the quote-unquote right way. Does that make sense? I create a new string builder, and I append the character that I pass in to that string builder n times, and return the contents of that string builder. So nothing real complicated. Just a helper method that makes things a little bit easier. So going back to draw asterisks, we have our doing things part. We have our recursive call or our approach, but we still don't have a base case. What's our base case? What is the case where it really doesn't make sense to do anything? Nope, that's our initialization. That's our starting point. But we drill down further and further, and there is a certain point at which it doesn't make sense to do anything. So let's start at 8 and work our way down. If width is 8, how many asterisks are we going to print out? 8. If, not that we will on this case, but if we had a width of 7, how many asterisks would we print out? 7. If we had a width of 3, how many asterisks would we print out? If we had a width of 2, we'd print out 2 asterisks. With width of 1, we'd print out 1 asterisk. If we had a width of 0, what would we do? Return. Exactly. That's our base case. If width, I'm going to say less than or equal to 0 because having a negative width makes absolutely no sense. less than or equal to 0, return. We don't even want to print 0 asterisks, because that would end up printing a new line and that would mess up the pattern. So that's it. The book says something about 7 or 8 lines of code. I don't think they made this n-char helper method. That's 4 lines of code. And that, come on. That looks like success to me. Any questions? And we can see how this compares with the implementation I wrote before class, and it's identical. Short-term memory, good. Long-term memory, not so much. Or I guess that's working memory versus... Never mind. Enough psychology. Questions on recursion? We have 15 minutes before break time. In those 15 minutes, I'm going to pull up my my implementations of, what was it? The most recent programming assignment that was due. I guess that would be 3. There were some questions on that. So let's see. For programming assignment 3, for programming assignment 1, we implemented instruction, and I did that in class. Programming assignment 2, we implemented program, which was basically just a linked list. Programming assignment 3 was the beginnings of the implementation of machine and a little bit of a stack, a stack to do math. There really wasn't much to the stack. From what I saw, that was everybody got that part. What seemed to be the most difficult part for everybody was the main program and the machine program. So, quick note about the main programs. They are not intended to do anything complicated. The main program does very little. It's basically just the interface between the code, the instruction language code that I dump in, and the machine that actually runs everything. So program, machine, arith stack, they do all the heavy lifting. The only thing that the main method does is convert this list of instructions, this bunch of text, into something that the machine can actually handle. So so we'll start there. PA3 main. And I'll open PA2 main and PA1 main as well. So here's PA1 main, the one that I did in class. And basically this loop runs while there is something to read in. If there's something to read in, it reads it in, discards it if it's a comment or a label. We're not dealing with labels right now, though we will later. Creates a new instruction and immediately prints it out. It does very little. PA2, a reminder, your main classes should be called main.java. The main class should be called main. I have mine called different names because I have them all on the same folder, all using the same stuff. Yours should be evolving as the semester goes on. Or you can copy and paste them to different directories and keep them separated. So instead of this named PA2 main, yours should just be called main. You can either modify that one or copy that stuff, save it somewhere. Or you're already zipping it up to email it to me. You can use that as an archive of what you've already done. So for PA2, the only changes, actually that might be interesting. There's a program on Unix called diff, which shows the differences between files. So pa1main.java and pa2main.java. So where's my mouse? There we go. Different class name, okay. I create an instance of my program class. Assignment 1 didn't have a program class. We didn't have any programs. But assignment 2, we have a program. We have to create a new instance of that. Here, instead of printing out the instruction after we create it, we add it to the program. And then we iterate through program. Iterating through program gives us one instruction after the other, and we just print it out. And as I mentioned in the programming assignment documentation, the output from PA2 should have been exactly the same as the output for PA1. So very little change between PA1 and PA2 in the main class. Just the addition of this line and the addition of this extra loop after this while loop. And I'm pretty sure that I mentioned when you're testing, if you're typing things into the Dr. Java interactions pane, if you type Control-D, that will act as end of file, and that will make standardin.hasnext equal to false. The way I accomplish that is I'm actually dumping a file directly into your standard input, and a file already has an end of file. A file has an end. So that character automatically gets dumped into your program, and that works as intended. That's also a Unix technique so that you can string multiple programs together. You can take the output of one program and dump it into the input of another program, and you can actually do that multiple times. I've had, these things are called one-liners, where you're stringing programs together. I've had them span three lines, multiple different commands. So the difference between PA2 and PA3. We added the machine class, and we need some call to run. So instead of having this for loop, which prints out the instructions in program instruction by instruction, we create a machine, send program into it, and call the machine's run command. So if we do a diff on those two files, apparently I commented those lines out. But we can see a difference in name. And the only difference is taking out this for loop, creating a machine, passing a program to the constructor, and calling its run method. That's the only thing that's different between the main for PA2 and the main for PA3. The main for PA4 and the programming assignment instructions say this explicitly, is exactly the same as the main program for PA3. That's the only time that'll happen, by the way. There will be slight changes to main for PA5, PA6, and PA7. So now I'll open up machine. And machine really, where is it? Machine. Is not entirely interesting. There's very little going on in machine. Even though it does a lot, it pretty much does all the heavy lifting of the interpreter. Everything is pretty straightforward. All the methods are 1 or 2 lines, with the exception of the run method, which is long and tedious. You can see I've already written, because I wrote PA4 so that I could write the runtime class. The PA4 stuff is in here. But for PA3, you need a program that the machine is going to run. You need an arith stack that's going to do the math. And one of the instructions of PA3 specifically says create a constructor that takes a program as an argument and saves it internally. That means you need an instance variable. You need to save the program that's passed into the constructor into that instance variable so that you have it when you call the run method. And it really doesn't matter where you initialize the stack, but you do need to have that stack initialized before you can push and pop things onto and off of it. You can do it equally validly right here when you declare it. Then we get into step 2 of that large instruction, which was write methods, private helper methods that have no return value, have a void return value, return type rather, called do and then the name of the instruction. Whether you use capital letters for your instructions or lowercase letters for your instructions, doesn't matter. I wasn't going to call these directly anyway. I couldn't because they're private. The important part is that you have one method for each type of instruction. Sorry, each operation of instruction. So you have a method to handle load instructions, a method to handle print instructions, a method to handle add instructions. And all of there were 12 instructions that you had to implement for PA3. All of them, except for load, did not take any operands. So there was a sentence in that instruction that said, if this particular operation takes an operand, an argument of that type should be passed to the method that handles it. So the only one that takes an operand is do load. For now, load loads an integer onto the stack. It just pushes an integer onto the stack. So it needs that integer from somewhere, which should be passed in as an argument. Because these methods know absolutely nothing about the actual instruction that is being executed. They're just doing a little bit of functionality. And every single one of these do something to the stack. Do load pushes something onto the stack. Print pops something from the stack and prints it to the screen. All of the other ones pop 1 or 2 values, do something with them, then push them back onto the stack. Do add, do sub, do molt, do div. You can see I took your strategy of fitting things into one line. You can do all of these in 3 lines. You can do them in 4 lines. It makes it a lot more readable. But we like challenges. Then everything else. So that was add, subtract, multiply, divide. So we've gotten through 6 of the 12 instructions. The last 6 were bitwise operations. These are operators that you probably didn't use in your last Java class, but you should have at least heard of their existence. Most tables that list all of the Java operators on them list the bitwise operators. And I think most of you weren't familiar with how to actually use them. What they actually do is take a something that is integer-like. So they work on ints, longs, shorts, and bytes. I believe they might work on booleans. I haven't tested that, but their functionality on booleans are essentially the same as their functionality on. They basically turn into logical operators, so they're not much use there. They do not work on doubles and floats. So it basically takes the bit representation of one number and the bit representation of the other number, compares them bit by bit, hence bitwise, and returns some number of the same type. If your stack dealt with doubles, you might have had some issues with this. If your stack dealt with ints, everything went fine. Bitwise AND is simply a single ampersand, whereas the logical equivalent is 2 ampersands right next to each other. Same thing with bitwise OR. Bitwise NOT is the tilde, whereas logical NOT is the bang, the exclamation point. Exclusive OR is caret. NOR, there were multiple ways to accomplish this. The assignment said that NOR is equivalent to performing an OR and then performing a NOT. If you called do OR and then do NOT, that would have worked exactly the same way as what I'm doing here. Because do OR would pop two things off the stack, compute the bitwise OR, push it back onto the stack. Do NOT would pop that back off the stack, complement it, push it back on the stack. Here I'm doing this in one line, but it's essentially equivalent. Do NAND is a combination of and then NOT. So it performs an and then complements the bits. Okay. So either implementation would have been okay. More stuff for PA4, which I'll scroll by. Now, let's scroll down and hide the PA4 stuff. For PA3, the run method was a loop. That's all that needed to be in the loop, in the run method. And it's basically the same loop as was in PA2 main. So this loop right here, for every instruction in program, do something. The loop body is obviously different, but let's go back. Well, that's interesting. Okay. So for every instruction in my instance variable is called the program. For every instruction in the program, first I get its operation, and I save that to a local variable just so it's easier to compare. I don't have to say I.getOperation =ignore case load. Yes.
I had that for the loop. I kept trying to compile it and I kept getting errors, and I would use the exact same format for that for you.
What?
I get a compiler error for each one applicable to expressions like math instruction, declare some variable name, and run my program for the file.
The only thing that I can guess by looking at this is that new program is the main program, which is a variable program. My guess is that program does not implement your interface.
you believe that will come from there, it's about putting in the same iterator. And that will,
Oh, yes. I should have noticed that. I should have told myself. Bank error. Read your paper. Okay. Right. So, program has to implement the iterator interface. Otherwise, that for each syntax will not work. And in fact, if it also needs to implement the it needs to implement the iterable interface in order for that to work. It needs to implement the iterator interface in order for you to be able to return it from the iterator method. So basically, it needs to implement both. But you get compiler errors in different places if you implement one and not the other. So then the rest of the method is just, it's basically an excellent opportunity to use a switch statement if Java switch statements worked on strings. So since Java switch statements do not work correctly, or the way we would want them to on strings, I have to do this nasty if-else statement. And you'll end up having to extend this for programming assignments 4, 5, 6, 7. I think not one of them somewhere in there, but all of the others. Basically, add some more pieces to this if-else-if mess. And really, all it is a switch port. Is this instruction a load instruction? If so, call doLoad and pass it the correct argument. Is it a print instruction? If so, call doPrint. And that's why each of those individual methods should handle everything pertaining to that instruction. Right. And that's pretty much the same for all of the instructions. I put an else at the end because there are some instructions we don't know how to deal with right now, and I just printed them out. So my output for the input that should have worked with PA3 was, I think there was a branch instruction. Then it should have printed out 10, and then there was another branch instruction. I know you got the right output, which was very odd because I'm used to the output for most of my programs being long. So when I saw a single number, I was like, is this right? It was. And if I go ahead and run this, so there it's prompting me for input. I'm going to go over here and so this was the test program for this was the test program for PA 1 and 2. The loop 1 to 10 takes out some of the instructions because they are currently not valid. You tried that.
Yeah.
It breaks horribly.
And it errored on me, and I looked at it and said something about an I, and I'm looking, oh hey, this isn't implementable right now.
Yes. Eventually, load will take either a string or a number. Right now, it only takes numbers, so if you try to put a string there, it all sorts of breaks. Loop with syscalls will be useful for PA4. It's necessary to test the runtime piece. So we'll use this loop 1 to 10. Right now it actually doesn't do any looping of any sort because I've commented out all those pieces. Actually, I think it would. If we had jump functionality implemented and none of the other functionality implemented, it would work fine. So I will paste that into standard input. And like I say at the bottom, this is what the output should be. I note that my run method has a default case that prints out the instruction if it doesn't recognize it. This is not a required part of any assignment, but is helpful for debugging. And then I need to type Control D, and it prints out exactly what I said it does. Say it does. Questions? So we're kind of running a little overtime, but not enough to cut it off now and then start over after the break. So very quickly, going through assignment 4. It talks about a runtime class. Looks like I lost a parenthesis here. As I mentioned last time, I posted it both as a Java file, Java source code file, and as the compiler class file. If you don't want to look at the source code, you don't have to. You can just download the class file, put it in the same directory as all the rest of your Java files, and everything will compile fine, at least pertaining to the runtime class. Or you can download the .java file, and it has some interesting stuff in there if you're interested. If you download the .java file, do not make any modifications to it, because I am going to dump my runtime class into your project in order to compile it. So if you don't use my runtime class as I have it written, bad things will happen. I also don't recommend editing any of that because we haven't talked about most of the stuff in there. It uses threading and stuff. So the actual assignment. It involves implementing a queue, which for me was just copy and paste. So there are 2 implementations of the queue in the book. I did one of them in class. It is not posted to the website, but I took my implementation that was basically copied from the book, since it uses generics, and dumped it right into my program. You need to implement a message class, which is very trivial. It has a single constructor, and it has 2 public instance variables, one of which is an array. So that's 4 or 5 lines of code. Class called Q, that's copyright out of the book. And then take your machine class and add 2 instance variables to it, one for runtime and one for the message queue. You don't need to have any accessors or mutators because nothing else in the world is going to use this stuff. It's just internal to machine. And you need to initialize it at some point as well. You need a helper method to handle the syscall instruction. So that's adding to that list of 12 helper methods. So now you have 13. And the functionality is described there. And you have to add another switch to your if-else-if mess to actually call that do syscall method in the right situation. Also, as part of the run method, you need to create a new variable of type runtime, or a new instance of the runtime class, and save it in that instance variable called runtime. Passing in the message queue, which I ask you to call messages, as the argument to the constructor. There is only one constructor on runtime. It takes an argument of type Q brackets messages. If you do not call the constructor like that, it will not compile. That is written like that intentionally. Before you have that while instruction in program, or for instruction, whatever you call it, in program loop, you need to start the runtime by calling runtime.start, and at the very end of your program, stop the runtime by calling runtime.stop. If you don't make those method calls, those method calls are not for the purposes of details that I'm going to grade on. Your program will not run correctly or stop when you tell it to, regardless of anything else you might do, unless you call runtime.start and runtime.stop. So before you iterate through the instructions in your program, make sure you call runtime.start, and when you're done iterating through all the instructions, make sure you call runtime.stop. Make sure you only call each of them once and in the right order, otherwise things will break. Any questions on that? All right, cool. So, 10-minute break. We'll reconvene at 3:20-ish. I'll look at some programming projects at the end of this chapter that look interesting and useful for practicing recursion. There's really not a whole lot to do with recursion. It's just take an example and try to develop a recursive solution for it. It's not the most interesting thing in the world. You're also welcome to work on PA4 and ask me questions about it. All right, break time.